How many times in your mathematical career have you dealt with projectile motion, which we call sometimes rectilinear motion? They give you they give you a quadratic function. They say this is the height of a flying object, um, assuming no air resistance. So you're looking at the graph and you say, oh, the graph looks something like this. And in an algebra class, when you learn how to do quadratic equations and whatnot, or factoring, they're asking you questions like, find the time when it hits the ground. So what you want to do is you want to set this thing equal to 0, because that's when y equals 0 is when you're on the ground. And so you're finding the two intercepts. So you're either using the quadratic formula or factoring or something. They may even say, find the vertex. And so in the vertex, you would have to rewrite this in vertex form as sort of practice to figure out where the vertex is. Then you go to calculus 1, and they say, hey, how fast is it moving? So you're looking at slopes of tangent lines. You actually find an easier way to find the high point, because you can just take the derivative and set it equal to 0. But where does this equation come from? I mean, they just give it to you usually and say, here, go for it. Right? Where does it come from? Well, here's where it comes from. Okay. In calculus 1, we talk about if you've got some function, let's call it s, some f of t equals some position function. Position, I don't know how many s's are in position, but as many as you want. Position as a function of time. Then the derivative, it's how fast your position is changing. It's the velocity. Okay. And the derivative of that, which would be the second derivative of the position, which is the first derivative of the velocity, which is what we call the acceleration, as a function of time, right? And you can keep going. You take the derivative again, you get the jerk, you get to take the derivative of that, you get the rate of change in the jerk, and anyway. But now I can work backwards. Rather than starting with the position and asking about velocity and acceleration, I can work backwards, because here's how it goes. If you say I've got an object that we're assuming no air resistance, the only force acting upon it is the downward force of gravity. Now, force is mass times acceleration, so I can think of acceleration as force divided by mass, right? I'm thinking over here, force equals mass times acceleration. It's force divided by mass. So anyway, generally I have got a constant mass, and gravity is pulling it downward, so the acceleration here is just the acceleration of gravity. Now, on a small scale, as in provided that the distance between the object and the center of gravity is not very far, is actually very far. So like an object that's held 100 feet above the surface of the Earth, when the distance to the center of the Earth is in thousands of miles, then the relative distance is very great, and we can assume that gravity is constant. So if the acceleration of gravity is constant, then I know that I can figure out something about the velocity. So let's put some initial conditions here. I'm going to tell you that the gravity is equal to, I'm American and I use feet and inches and all that kind of stuff. So I'm sorry to you people doing physics that do it all in metric. I'm going to use that gravity is 32 feet per second per second. It's the acceleration of gravity. And let's start off with something like at time 0, the position of this object is, what did I say? I said 100 feet above the ground, right? And let's throw it upward at a velocity of, let's say, pick a number, it doesn't really matter. Let's no, 30 is not that good. How about 20 feet per second, right? So it's starting off up here at about 100, and I'm going to throw it upwards. All right, so it's going to go up, and then it's going to come down. So I've got this information and this information. I can get the position at any time, right? Because I know that the derivative of the velocity is 32, which means that the velocity must be an antiderivative of 32. So the velocity must look like 32 times t plus some constant. Well, what constant? This is where I use my initial condition. I know that the velocity is 20 when I plug a 0 in for t. And that would tell me that k is equal to 20. So my velocity now is 32t plus 20. Knowing that the acceleration was constant, I find an antiderivative to get to velocity, because back last quarter in Calc 1 I would have taken a derivative to get from velocity to acceleration. So this allows me to work my way back up. Taking an antiderivative always throws in this plus c or plus k. I don't know why I use k for constant today, but anyway, I did. And then I need to know something else. There's a lot of functions whose derivative is equal to 32. I want the one that when I plug a 0 in for t, it gives me 20 as the output. So that figures out what the constant is for me. Now I've got the velocity, but I know that the velocity is the derivative of the position. And all of a sudden, I'm going to change my mind about things. Gravity is pulling downward. This arrow is pointing downward. That the acceleration is actually in the negative direction. And so I really want this to be negative. Sorry about that. And so I really want this to be negative. And all it does is it changes this from negative. It didn't really change what k is, but these are all negatives. Gravity is downward. It's accelerating the thing in the negative y direction. So that gets me to here. Now, ds dt is this, so how do I calculate s? Well, if I've got the derivative of s, then I need to take an antiderivative. I got a linear function here, so I've got a minus 32. The t antiderivative would go to be t squared over 2. The 20 is 20t, and then there's plus a constant. Okay. So I'm going to go back and use this bit of information that at time 0 now, the height was actually 100 is what I wanted. So using that information, 100 equals, and I'm going to 32 divided by 2 is 16. So minus 16t squared, but t is 0. 100 is when I plug a 0 in here. Plug a 0 in there and get plus c. Well, in this case, c is equal to 100. So s is equal to minus 32. Actually, let's just divide here. 16t squared plus 20t plus 100. If you know the acceleration, you know a starting height and a starting velocity, then you can work backwards using antiderivatives to get what the equation of the height function is, right? And this is why you always had a quadratic function describing your height function. If you assume gravity is constant, then velocity is linear, and my battery is running out, and the function is quadratic. The height function is quadratic. So I'm going to stop right here, plug in my computer, and we'll see you on the next video.